In this section, we're going to take a look at power series. Now, a power series is a series of this form here, where this c sub n is just a coefficient that depends on n. In other words, that depends on which term in the series you're looking at. And then the other thing to notice is that all of a sudden we have an x here. Okay, so this is new. We have the variable x showing up. So to maybe make this a little less strange looking, because this is strange, we're mixing up now potentially n's with x's. Let's try this. How about n equals 0 up to 2? And I'm going to write down the formula 1 over n plus 2 times x to the n. So this, the 1 over n plus 2, that is the Cn we're talking about. So we're going to get a different coefficient for every power of x that we write. So as I write this out, when I plug 0 in for n, I of course get 1/2. And of course x is to the 0 power, so that's just 1. When I plug 1 in for n, I get 1/3, and then x to the 1 is just x. And then lastly, when I plug a 2 in, I get 1/4 x squared. So if I do this series just from 0 to 2, then you get this quadratic polynomial here. Okay. So what we're going to be basically looking at in the long run here are infinite polynomials, right? We've studied polynomials in the past, and you'd always stop at some power as your highest degree term. And so here we can potentially go on forever and then study those objects. All right. So we also kind of more generically can talk about a power series centered at A, and that's just where you have x minus a instead. And so just think of this as when you have an x minus a, just basically taking this and shifting it over a, right? Shifting it to the right by a. So this would be the power series centered, I should point here, I guess. This would be the power series centered at 0. And then this one is the power series centered at a. So this is just a more general form of that. And this will be important to us as well as we continue on. And ultimately where we're going with this is it's going to turn out that a lot of the functions that we know and love can be represented with particular power series. Okay, it's going to turn out, for example, that the function e to the x is going to have a power series representation for it. Okay, and this is going to be really handy for a variety of reasons. Okay, but that's getting a little ahead of where we're at right now. Right now we just want to study this thing that we call the power series. All right, so let's do a concrete example here. For what values of x does the series converge? Now, let me just say this first of all. Let's not let this x throw us off too much. X can be any number we want, right? So like just for example, I could say if x equals 2, then the series that we're talking about is the series n equals 0 to infinity 2 to the n over n factorial. Okay, so this is a series that you might have seen in the previous section that we studied, particularly when we started looking at the ratio test. So we're used to this. all we're saying now is, what if we plugged in other numbers instead of 2, right? So if I said, if x equals 3, then that is a brand new series. And so if I'm allowed to put different numbers in here for x, that kind of begs the question of, okay, are there some numbers that I could plug in that would make a convergent series, and then other numbers that I might put in that would make a divergent series? So we're gonna try to study that. So trying to determine that, what numbers I'm allowed to put in, is called finding the interval of convergence. And then the radius of convergence is the length of that interval that we find. Okay. So in order to do this, I already kind of let slip the strategy we want to use. We want to use the strategy of applying the ratio test. Okay. So remember, in the ratio test, you take the limit as n goes to infinity of a sub n plus 1 over a sub n in absolute values. Okay? And so if that answer exists and is less than 1, then you have convergence. If either it equals L, a limit that's greater than 1, or if it does not exist, remember that's when we have divergence. And then there was the middle ground. What if it is equal to 1? And then remember, in this case, we don't know. We don't know by the ratio test. That doesn't mean you can't figure it out, but it just means the ratio test doesn't tell it to you. Okay, so that's what our ratio test is, remember? So if I'm interested in finding when this is convergent, then applying the ratio test might make sense, because I'm going to have this expression that involves x, and maybe I'll be able to look at it and see for what values of x I'm going to get a limit that's less than 1. All right, so let's set this up. Let's take the limit as n goes to infinity of the absolute value, and then I want to plug n plus 1 into both of these slots up top. So this will be x to the n plus 1 divided by n plus 1 factorial, and then on bottom x to the n over n factorial. All right, now when we applied the ratio test before, remember we wanted to clean this up, so maybe take the bottom fraction, flip it, and multiply it. And also we wanted to limit our use of the absolute values. In other words, if a part of the formula doesn't need an absolute value, let's not put it there. So the n plus 1 factorial and the n factorial, those are definitely positive numbers. But the x, that might be different, right? That might have, that you could have negatives in there. So here's what we're going to do. We're just going to collapse the absolute value down to just the x, so that it's positive, over n plus 1 factorial times n factorial over the absolute value of x to the n. And sorry, shame on me, I forgot my limits here. Let me fix that real quick. I could probably squeeze it in here. So equals the limit as n goes to infinity. Okay. So with that, now we see, what can I do to simplify things? And you saw some problems that were like this back in the last section, where we said, okay, if I have something to the n plus 1, that can be that thing to the first, right, times that thing to the n, right? Multiplying like bases means we add exponents. And then remember with factorials, we learned that n plus 1 factorial could be written as n plus 1 times n factorial. But of course now we have all sorts of nice cancellation that's possible. So let's cancel what we can. I can cancel out that, and I can cancel out those. And so as I do that, all I'm left with is the limit as n goes to infinity of the absolute value of x over n plus 1. Now, remember, what we're searching for is what numbers could I put in for x that will give me a limit less than 1. Well, if I put in a 1 for x, 1 over n plus 1 goes to 0. If I plugged in a negative 5 for x, then that would become positive 5, right? And positive 5 over n plus 1 goes to 0, right? So I'm just going to keep track of the things I'm trying here. What if I put in a million for x? Okay, so literally 1 million over n plus 1. Well, eventually, once n gets significantly bigger than a million, what's going to happen? This thing goes to 0, right? So as n goes to infinity, right, these are all going to 0. So here's what this means. This limit is equal to 0 for all x, right? It doesn't matter what x you choose, this limit goes to 0. And by the ratio test, that means no matter what x we choose, it will definitely be a convergent series. So what we can say here is that the interval of convergence is negative infinity to infinity, right? You can plug in any real number. It doesn't matter what you plug in here. This is always going to be a convergent series. All right, so let's try another one here. So we've got the series negative 1 to the n times x minus 2 to the n divided by 4 to the n. So just a little note here, if I backtrack to the first page, this one would be the power series centered at a, or centered at 2 in this case. All right. And by the way, this whole idea of centering at 2, understand that if you plug x equals 2 in here, you're going to get a very boring convergent sequence, right? So the idea is where it's centered at, well, of course it's going to be convergent there in the trivial sense, right? And that's that kind of that idea of centering it at 2. All right, so let's look at this. We're going to do the ratio test again. So we'll take the limit as n goes to infinity of, and so everywhere I see an n, I put an n plus 1 up on top. And then on bottom, I just put everything with n's. All right. And then remember what we're going to do is we're going to only apply the absolute values to the things that actually need it. So we're going to say this is equal to the limit as n goes to infinity. And I'm going to put absolute values around this because this can produce a negative, and I'm going to put absolute values around the x minus 2 because it can produce a negative. So I'm going to end up with negative 1 to the n plus 1, the absolute value of x minus 2 to the n plus 1, all divided by, and then I don't need to bother with absolute values here, right? That'll always be positive. And then I'll multiply by the reciprocal. 4 to the n doesn't need the absolute values, but then negative 1 to the n, and then x, absolute value of x minus 2 to the n. Now, this business that I just did here with the negative 1, you can, I would be totally fine with you skipping over that step, right? Because just by glancing at it, we know that it's just going to be 1 or negative 1. And so once you take that absolute value, that's going to equal 1, and that's going to equal 1. So if you want to not even bother to write it and just drop it out, that's okay with me. All right, but then just like in the last problem, what can we do? How can we rewrite it so we can see things canceling? So I've got on top there x minus 2 times x minus 2 to the n, right? And 4 times 4 to the n. So similar techniques to what we used in the last problem. And a lot of nice stuff cancels out for us here. So that's going to cancel, and that's going to cancel. So notice everything with an n cancels in this particular problem. So the limit, as n goes to infinity, the n's kind of irrelevant. This is just going to equal the absolute value of x minus 2 over 4. So now we go back to the ratio test, right? In the last example, I wrote out the ratio test, right? So what are we looking for? When the limit is less than 1, it's convergent. When it's greater than 1, it's divergent. And when it's equal to 1, that's when we don't know. Okay, so let's start with the easier part. How can we make this thing less than 1? Okay, so convergent, right? If the absolute value of x minus 2 over 4 is less than 1. But of course, that would have to mean the absolute value of x minus 2 is less than 4. But let's keep in mind what absolute value really means, right? Like, yes, it does always turn things positive. We know that that's the case about absolute values. But at its core, it's telling us how far away from things we are. So x minus 2 in absolute value is saying x, how far is it from 2? So we're saying that we want the x's so that the distance between x and 2 is smaller than 4. So what that means is that x minus 2 could be smaller than 4, but it also has to be bigger than negative 4. Okay, or perhaps what's good here to do is to draw a little picture to remind us of why we set up absolute value inequalities that way. So here is, well, here's 0, and then here's 2. Okay, so the idea is, how far can I go this way from 2, right? And how far can I go this way from 2? Well, if I need to be within 4, then that's saying that x needs to be between negative 2 and 6. And that certainly looks like what we want to do. So we're saying we need the absolute value to be within 4. So you can go 4 in either direction from the number 2. And then that leads us to this inequality. So what we know is that it's convergent definitely for negative 2 and 6. Okay? But you know what we also have to do? We also have to address the one part that the ratio test doesn't know for sure. We have to address what happens when the limit equals 1. So we're also going to say that it might converge if x minus 2 over 4 equals 1, right? So when the limit equals 1, we don't really know. Okay, so let's see when that happens. Well, this would be x minus 2 equals 4. So, right, so on the one hand, x minus 2 might equal 4, but on the other hand, it might equal -4. So that gives me x equals 6. And that gives me x equals -2. Now, of course, note what happened was that was just the two endpoints here. So we'll just note that. So what we need to do is check the endpoints for convergence. And so the idea here is that we don't know by the ratio test if they're convergent, but what we can do is just take them at face value and just take a look at the series. So for x equals -2, let's plug it in. This would be n equals 0 to infinity of -1 to the n, -2 minus 2 to the n, divided by 4 to the n, which is just going to be n equals 0 to infinity, -1 to the n, -4 to the n, over 4 to the n. And you know what, if I wanted to here, I could pull out a -1 from that. Right? -1 to the n times -1 to the n times 4 to the n over 4 to the n. And a -1 times a -1, of course, is going to be just +1. But then, of course, my 4 to the n's are canceling. Right? And this might seem like a strange series that we're left with, but this just ends up becoming the sum from 0 to infinity of 1. All right, well, if you sum 1 over and over and over and over again, would you agree that that is divergent? Right? You're not going to settle down on a single number that it sums to. And x equals 6. Okay, so n equals 0 to infinity, -1 to the n, 6 minus 2 to the n, over 4 to the n, which is -1 to the n, 4 to the n, over 4 to the n. And again, we get some nice canceling here. But then all you're doing is you're adding -1 to the n up. Or in other words, you're alternating between -1 and 1. So if you go -1 plus 1, you know, plus -1 plus 1 plus -1 plus 1, of course, that is also going to be divergent. So what we've done here is we've checked both of our endpoints and found them both to be divergent. And so what that does is it says we're finding, if we want to find the radius of convergence of this series, the radius of convergence was, and I actually already had the answer right here in 4, is 4, because I can go 4 in any direction from 2, or I guess, less than 4 in any direction from 2, and I get convergence. So here's to kind of summarize. The radius of convergence is 4, because that's how far away I can stray from 2 or up to 4. And then the interval of convergence, even though it wasn't explicitly asked for, you will usually be asked for it. The interval of convergence is this interval we found right here. So it'd be -2 to 6, where we don't include -2 and we don't include 6 because we found the series to be divergent in those places. All right, so we've seen a couple of examples, and here's a little theorem to kind of wrap up what we've got going on here. It says, for a given power series, there are only 3 possibilities. The series converges only when x equals a, right? It's always going to converge then because you're causing a 0 to happen right there. It converges for all x. This was our first example. Or there is a positive number r such that the series converges if the absolute value is less than r, and diverges if it's greater than r. So that was what happened in our last one, right? So the this absolute value here was less than r, right? So this was the x minus a less than r. All right, and then our little note here is what we did at the end, where it said, since the ratio test gives no information when the limit is 1, we must check the endpoints to determine if the interval should or should not include those endpoints. All right, so let's take a look at example 3. So we're going to find the interval of convergence for this series. All right, so we know the drill now. It's all about the ratio test. The limit as n goes to infinity of x minus 5 to the n plus 1 divided by n plus 1, 3 to the n plus 1, all divided by, make this a bit bigger here, x minus 5 to the n over n times 3 to the n. So n plus 1, n, 3 to the n plus 1, 3 to the n, none of those could ever be negative. So we're only going to put the absolute values on the x minus 5 up here and down here. So this is going to be the absolute value of x minus 5 to the n plus 1 divided by n plus 1, 3 to the n plus 1, times the reciprocal of what we have down there, absolute value of x minus 5 to the n. And then let's see what kind of simplifying we can do for ourselves. Up here, x minus 5 times x minus 5 to the n. And then down here, can't do much with that n plus 1 here, but I can definitely do something with the 3 to the n plus 1, right? Breaking those apart using our exponent rules. And then up here, n times 3 to the n, x minus 5 to the n. So we do get some canceling happening here. So those are going away for me. Those are going away for me. All right, so let's see what I'm left with. I think to kind of organize myself, I'm going to gather up the ends and the non-ends and kind of put them together. So this will be the limit as n goes to infinity of x minus 5 over 3 times n over n plus 1. Now, I want you to remember back in Calc 1, remember that if you had a constant inside the expression you're trying to take the limit of, you could always pull that constant outside the limit, right, if it didn't have your n involved. And so this thing, as far as n is concerned, is a constant, right? I know it's got an x in here, but that x is what we're ultimately going to try to solve for. That's not the n we're using in the limit. So you can pull that outside. So this is x minus 5 over 3 times the limit as n goes to infinity of n over n plus 1. All right, and that n over n plus 1, remember, we hopefully kind of know where that's going, right? N and n plus 1 are basically the same in the long run. So it should all head to 1, but remember, to make it formal, you can always multiply by 1 over n on top and bottom. So this becomes x minus 5 over 3, the limit as n goes to infinity of 1 over 1 plus 1 over n. And that is just going to equal 1, right? So our answer is just the constant that's outside. All right, so what do we know, right? We know that it is going to be convergent, right? Convergent for sure if the result of that limit is less than 1, which means x minus 5 is less than 3, which means that x minus 5 has got to be something between 3 and negative 3. So that lands x between 2 and 8. Now down here, I can get most of my answer. So when they asked for the interval of convergence, I can definitely say that I'm going to go from 2 to 8. The only question is, does 2 get to come to the party? Does 8 get to come to the party, right? Or in other words, are we convergent or divergent at the endpoints, right? So we're saying that the ratio test, remember, inconclusive when x minus 5 over 3 equals 1, okay? Or in other words, when x is equal to 2 and x is equal to 8, right? So at those endpoints. So we're going to check each one. Let's check x equals 2, right? And here we're just plugging it right in. N equals 1 to infinity. 2 minus 5 to the n over n times 3 to the n. N equals 1 to infinity. And so this is going to be negative 3 to the n over n times 3 to the n. But then if you have a negative 3 in there, you can always pull that out as long as you keep the negative 1 raised to the n. You can write it like that, right, by our exponent laws. And so what happens there is those 3 to the n's cancel. And so what we're left with here is n equals 1 to infinity of negative 1 to the n over n. And I'm not going to go through the detail work here, partially because I'm out of space, but remember that this guy is an alternating series. The limit of 1 over n is 0, and each term gets smaller and smaller. So this is convergent by the alternating series test. So here's what that means. As I go down here to write out my interval of convergence, when it comes to x equals 2, I am going to include it. Because if you let x equals 2, the series will converge. So I have a bracket here, since it converges for x equals 2. So now we're going to check the other one. Let's check x is equal to 8. So if I plug 8 in there, eight minus 5 is 3, so this is going to be n equals 1 to infinity, 3 to the n over n times 3 to the n. And then if those 3 to the n's cancel out like we know they do, then we're left with what should look very familiar, right? This is our classic series where the terms get smaller, but it diverges, right? Because it's a p series with p equal to 1. I'm going to write that in red to make it abundantly clear here. So this is divergent since it is a p series with p equal to 1. And so because it's that x equals 8 produces a divergent series, then we use parentheses there since it diverges for x equals 8. So the moral of the story is we're using the ratio test, we're calculating the limit that's produced from the ratio test, we're setting it less than 1, right? So we're setting it less than 1 because we know it'll be convergent there and solve for x. And then the endpoints are tricky. We just got to plug them in and see what happens with the series that's produced when you plug those in. Sometimes you include, sometimes you don't, right? In the previous example we did, right, we didn't end up including either of them, right? So there's no hard and fast rule here necessarily, but we need to make sure that we're checking both endpoints each time.